Hi everyone. In this final video, I want to go over one quick example if the ratio did exceed 100. So in the previous example that we did, a ratio did fall between 22 and 100, and that is therefore why we were able to use the approximate evaluation of slenderness. Now let's say if the ratio was over 100, the code does say that detailed second order analysis is required. For this, we can go to Midas and use the p-delta analysis. And that is what I will show you. And also in this video, I do want to show also the buckling analysis that can be done within Midas if you do want to compare our buckling load. Okay. So our model. And the first thing we want to do is go to analysis, click P delta, and this will pop up. The number of iterations and the convergence tolerance. We can keep these as default. These are just depends on how many times you want to run the iteration. And then let's just add our load case. Permanent, another, add. Okay. Now, let's run it. Our results, forces, beam diagrams, and let's just individually see each load case first. Let's click values legend. Let's update it to be fixed, not scientific. And here we go. We see that our applied was 80, and now the magnified is 9380. Let's check the other direction. It was 100, and now it's 117.3. Others really quickly. 600, now 703. And in the other direction, 200 to 234. Okay, so now let's check the full load combination, and let's compare it with the magnified moments that we got in the approximate evaluation, and we can see which one is more conservative than the other. So first we have 328.5. When we use the approximate evaluation, we had 344. So we can see that the approximate evaluation is more conservative. Let's just do the other direction so we can definitely see MZ. And we see that here it's 821. So really, the calculation showed us that it was 1429. So we can see how this approximate evaluation can definitely be conservative at times. Right. Now, I will move on also to how we can check the buckling load. And let's check this one here. Now, to check our buckling load, we can close this. We will have to delete our p-delta analysis. Let's delete that. Go to analysis, and now we can click buckling here. Under buckling, we can define our number of modes. We can leave the 0, 0, and then we'll just again apply our load cases. Let's say 2. Let's others. Okay, and let's run it. Now, once we see the results, we go to mode shapes, click values, legend, and here we have our critical load factor. So now what does this mean? This means if you multiply this load factor by the axial load that you applied on your model, that will give you your buckling load. Now, this will not match your calculations, and I'll show you why. The equation to calculate the buckling load is simply pi squared EI over KLU. However, when we used our flexural stiffness, we actually decreased our we actually decreased it by this factor and by the 2.5. And this is usually done because creep effects are approximated in design by reducing the stiffness. However, since this is just doing the analysis in Midas, it is keeping just E and I. So if I were to, let's just remove that really quickly so I can show you. Just have that. We see that we have 7,462, but the program also uses the theoretical design value, not the theoretical effective length factor, not the design. So let's make this 2. And we see that it's 8,227. Here, it matches. If we were to multiply 8.25 by 1,000, it is 8,250. So that is very close to this buckling load. That is how you can also check the buckling load. And that is the end of the column design within Midas.